Talk of the last day of this program, and it's my pleasure to introduce Houduo from Southampton and his talk on spherical Euclidean distance embedding.
Okay, thank you, Miha. First of all, I'd like to thank you for talk, and secondly, I'd like to thank the organizers. Some of them are here, and also for the Newton Institute for supporting me and to take this workshop. Oh yeah, yes, I should. Okay. Is it working? Yeah. Okay. Actually, today's talk actually is not my area, research area. I come to this polynomial optimization. Many people talk about graphs, and I was interested in the distance embedding problems. I found after I came here, I found that from the graphs, there are many geometrical embedding problems. So I picked a couple of them, and I studied them, and I got some awkward or interesting results. So today I'm going to show you. Probably you can give me some suggestions. The first part, actually there are two parts. First part, I give you a brief introduction. What led me here to study the graph problems, and which is about Euclidean distance matrix. Then I'm going to talk about the graph problems. So actually, my problem is very simple. I would like to place the points on a sphere, hypersphere if the dimensional space is higher, and but the data and follow certain patterns. Okay, that means you have a constraint on those data, and obviously this sphere depends on the center. If you know the center, the problem is simpler. Okay, if you know the radius of the sphere, then it's simpler. But the most interesting part, applications, are those cases where you don't know the dimension of the space, you don't know the center, you don't know the radius. Okay, actually you don't know anything about this sphere, and
so these are.
This is the space of the sphere.
And where is an R2?
All right. Okay. So I changed the last minute. This should be D. This should be D. so because I changed the notation somewhere, I'm going to use R in my talk. So I changed there. Yeah. Thank you. Okay, so that is the problem that is in my mind. Okay, I try to solve the problems of this kind. We will see in graphs, we have a problem that we don't care about the D. We know the center is at the origin. Okay, it's much simpler a problem. So the notation is standard, is very simple. You have matrix that is the element is positive everywhere, and the diagonal is 0. I call such a matrix is called a pre-distance matrix, and those are the standard notation. There's 1. Those is the symmetric matrix with the diagonals being 0. So the hollow space in linear algebra, what they call. And so the Euclidean distance matrix is defined in this way. If you can find the point, a point in this space, Euclidean space, so that every element is the distance of 2 points and squared. So the distance is a squared distance. And we will see why I use a squared distance shortly. And the people interested in how you can get this embedding space. So the smallest such space is called embedding space. So in real applications, you know the distance. you want to find those points. You want to find the Euclidean space, and also you want to find those points. So this is the triangle, the cone of the Euclidean distance matrix. So this those body actually contains every triangle triangles. For example, if you have a right angle triangles, you would have A, B, and C. So we all know that because we are dealing with the squared distance, this is the linear equation. That's why in the middle of this body is a flat, is a plane. That's the linear plane. Okay, everything else is just the curve. Okay, so that is the triangle if you use a squared distance. Okay, so basically optimization problem is this: you want to minimize or maximize objective function over this body. Sometimes you have to cut because you want a low rank, you want a certain constraint. So the optimization actually you optimize something, and you have to sometimes you use a hyperplane to cut this body and to find the optimal solution. That is the case that often appears in application. Yes.
So I think it's only convex if the dimension is not fixed, right? So if you put a bound on the dimension,
this is three-dimensional. That's yes.
Not 3 points.
3 points.
Embedding dimension is not fixed.
Embedding dimension.
This was the question.
Embedding dimension. Yes. No. You can. Yeah. There are many embedding dimension spaces. Yes. You are right. You are right. Okay. Yes. Probably. Attending this workshop make me feel less clever, and because you guys are very clever. Okay. So why consider the squared distance. This is the very famous result. I quite like it. And in Annals of Mathematics in 1935 and following, and the Schoenberg and Young and Householder in Psychometric in 1938, they independently discovered this. If D is a squared Euclidean distance matrix, then D, of course, the diagonal is 0 because it's a distance matrix. And then this matrix, okay, this is the E is a vector of ones. This is the projection matrix. You multiply before and after this matrix, and this matrix you negate this matrix. This is the positive semi-definite, and this is if and only if characterization. And furthermore, if you decompose, you do the spectral decomposition of this semi-definite programming, you have to half of this. And then those matrix P contains the coordinate. Okay? Actually, you can find the embedding point that give you this squared distance. So that is the classical Euclidean distance matrix characterization. They're very simple. So any questions about this? So this this characterization actually is very famous actually, and it's called classical multidimensional scaling in data reduction field. And the reason is that it's very simple, because the first step you just verify whether the matrix is the Euclidean distance matrix, then you do the spectral decomposition, you recover those embedding points. And but for this characterization, because we are optimizer, and we know this because the 0 is the eigenvalue of this matrix, and the select condition never satisfied. And later on, if you use semi-definite programming to solve certain problems, and the select condition is a restriction for such a method.
But you can just drop one column, one row.
Oh yes, yes, you're right. That's the one way the people propose to. But you would introduce extra linear constraint because you get rid of one dimension, and you would
Using the equivalent matrix instead of J, which would take it down to spatial reduction.
A rectangular matrix.
Yeah.
An n-1 times n matrix instead of the projector.
I think that's just like fixing one of the points, isn't it?
Yeah, you can fix one of the points at the origin.
Yeah.
Oh yes, yeah, of course, yes. And actually, what I didn't say there, that's observation. Actually, this classical method actually is this. For example, Young and Houduo, they just fix the first point on the x, the first axis, and that means you fix one dimension. And later on, actually, this characterization later on you use the center of all the points. You fix that center. Yes, that's why you have a projection matrix. Yes, in real applications, for example, this sensor network localization problem, you only know the partial distances between the points. You don't know. Previously, the Schoenberg, Young, and Houduo method, and you need to know every pair, every distance, all the distances. But in reality, you only need to know partial of them, and some of the distances have noises. It's not an exact distance. And so what can you do about it? Can you recover the location of those sensors? And the four big points in the middle are called anchors. So I just use this example. So of course there are many methods. I think Andrews has Miguel Andrews, and you had EDM survey paper, I think, a long paper, I think. I don't remember because I don't have a paper on the in the office, so I couldn't write down the exact date, the time. So I think the Euclidean distance matrix completion and semi-definite programming, and and also panel, and you can solve such problems. But let me just pick one that is very popular for engineering and computer science research. So in 2000, and Tottenham and Silver and Lanford, they published a paper in Science, and the citation probably is more than 2,000, probably is over 2,500 probably. And many people use this method. It's called isomap. So what they do is this. All right, and they treat this problem as a network problem, a graph. Okay, and some distances are missing. Then they say, all right, those distances are missing. I replace those distances as the shortest path distance, because you have a graph. You can calculate the shortest path, and you use the shortest path to for this distance between those two sensors. Then, so you use the shortest path for the missing distances, and then you use Schoenberg-Young Houduo decomposition to recover the point, the embedding point. The extremely simple proposal, and that's why so many people like it. It can be implemented a few lines, and it works for many problems. But probably I just use a toy problem to say there are certain drawbacks. For example, this is a triangle problem. We miss, this is unit distance, and one, this is unit distance, and we only miss this distance. If you use shortest path, this is 1, this is 1, the shortest path is 2, and you square it is 4, all right? So you square it, it is 4. And then you use the spectral decomposition, and you recover those points. You can see this is not a right triangle anymore, all right? And that means sometimes you may have trouble when you don't use accurate distances, all right? But of course, optimization people say, all right, we recover this distance. That's why we have a problem called computing the nearest Euclidean distance matrix. You're giving a distance, and this matrix contains missing distances. You may treat the missing distance as 0. You want to find a true Euclidean distance matrix, and so that this the rank, because remember the location, the Schoenberg and Houduo theorem said that this is the negative is the positive semi-definite. The rank is the embedding dimension. Okay, we ask the rank to be less than R. Okay, so if you do this, and you have a quadratic SDP. Okay, I think a panel can solve such problems. It's a quadratic SDP, and
But it's not convex.
no, you don't. Yes, you are right. You are right. Actually, SDP they just drop this constraint, and also there are some heuristic to induce the rank. They have tricks. They have. That's you would have a convex quadratic semi-definite programming. So, if you do that, and you would recover that distance, and I used one of my developed method. Doing that, you can see the embedding is like this. It's triangle, it's nearly triangle, a right angle decomposition, and the 3 points are on one line, and it is just a transfer of the original graph. Okay, and so the quadratic, the optimization actually can.
You got this result without rank constraint?
With rank constraint. With I used the method called embedding the distance matrix, and in my method, which I didn't talk about here, I force the rank constraint. It's not a convex problem.
And you know what result would you get if you just forget the constraint?
Forget the constraint. If you forget the constraint, and that's the convex problem. Something here you might change. You might change a little bit. Still, the convex solution is the starting point for my method. I use this convex problem solution as the starting point. The good thing is that convex programming problem provide a very good approximation to the final solution. But you can design problems that fail convex optimization, programming problem formulation method. But the method that I mentioned in the last slide actually use this characterization. I quite like this. And Hayden and Wells in 1990, and those two statisticians, and they come up with this characterization by studying alternating projection method. And this is one of their examples saying that alternating projection method is a powerful method. And look at this. This D is a Euclidean distance matrix. Then D is the intersection of a subspace with a cone. Okay? If you can put it that way, you can obviously use alternating projection when you calculate the nearest Euclidean distance matrix, because the objective function is distance, is the projection. Okay? And those people, they use this as an example, showing that alternating projection method has many applications. And look, this is the cone, and this cone, this is the symmetric matrix, positive semi-indefinite unit on this subspace, the orthogonal to the vector of all ones. And in polynomial optimization terms, which I learned through this workshop, it is a projected spectrohedra, because actually this is equivalent to with constant t and non-negative, such that this is positive semi-definite. So you project this first part to that. This is the projected spectrohedra. If I use Peter's talk, and he called this, I think it's a set called positive. And that's something I learned here. So if I use this characterization, I would have this, all right? And it's very interesting because if you deal with this constraint, the projection to this cone has a very nice formula, okay? The projection to this cone, but I didn't go into that part. Now, this is the first part. The first part, look, we have a distance. We want to minimize we want to find the best Euclidean distance, which is from the given one. So that is the background that I have. And now, this is the second part. I want to deal with the spherical constraint, okay? The spherical constraint is that, okay, the length of this vector is constant, okay? Though we don't know the number, but we know they are all equal. And what I do is this. I introduce the center of the sphere as another point, at one more point. So every other point to this new point is equal. The distance is equal, so that it is a sphere. Okay, every point stay on the sphere centered as at xn plus 1. Okay, the last point. So that is the constraint, the way how I deal with it. Then I have to work with the one more dimensional space. Okay, the Euclidean distance matrix now, pre-distance matrix now is in a minus 1 because you add one more point. Okay, and this is look, this is x1, x2, xn plus 1. So those are distance along the diagonal. So this is 1, the squared distance. This is 2. So the constraint I like to enforce is that I ask them to be equal, so that every point stay on the sphere. Okay. So this constraint actually is, look, this is a very simple constraint. It's linear. It's just in hyperplane. It's a very simple constraint. And now everything else stays the same. The cost, the price is this. I have to work with one more dimensional space. All right. And so let's assume that we have an objective function, or to minimize or maximize. Now, assume that we can solve such a problem efficiently. Now I come to the graph problem. So one of the graph problem that I come across is this: the smallest hypersphere representation of a graph. So probably you would know more than I do. And you have a graph, okay? You have a point. You want to have this is definition, all right? So you have a unit distance representation of a graph. Okay, this is capital G. And actually, it's the system of a point. Those points, and the distance between them is 1. The Euclidean distance between them is 1, and for any edge, okay, for any edge in this graph, this is called unit distance representation if the point if the lengths of the point are equal, so it is called hypersphere representation of G. So you would have two types of constraint for such representation. You would have, you place all the point on the sphere, and any edge, any point, any 2 point, which corresponding to edge, the distance has to be 1. And for example, this is the Peterson graph on a range, on plane. You see every edge has a unit distance, but the points are not on sphere. Okay, actually you cannot do that. Embedding Peterson graph on a plane, asking all the points on a circle and with the distance being a unit, being equal. Okay, you cannot do that. Okay, in 2-dimensional space. And I'm not sure. Probably you should at least use 4-dimensional. 3-dimensional is also not possible. I think. I don't know. It's I just read some papers and I didn't mark down the reference. And this is another one. This is another one. Actually, I took this formulation from this paper, Silva and Levin Tongso, and he got a paper saying that if you calculate this can be formulated, calculating the smallest sphere representation, you find the sphere with the smallest radius, and actually can be formulated as semi-definite programming. And this is because you are dealing with the positive semi-definite matrix, and the diagonal actually corresponding to the radius. Okay, all the diagonals equal, they are equal, and this is the any 2 points. The distance between 2 points equals 1, and this is positive semi-definite. Look, for such problems, you don't have a rank constraint. You don't have the dimension of the embedding space. Okay, this is a very nice thing to have. And interestingly, this quantity, the radius, the smallest radius, has a relationship with the Laplace theta function, and it has this formula. And actually, if you want to calculate this number, actually you can calculate this, compute this semi-definite programming. The interesting thing is, I asked Franz Randall, his office was next to mine. I asked why I didn't see many people solving this problem in semi-definite programming. And this formulation is known to people, many years now. And why I asked why don't people just solve this problem? It has some advantages. If this is sparse, this is dense, this is sparse, you would have less constraint. Okay, and Franz Randall told me that probably people don't like such a constraint. Though it's linear, and when you use SDP solver, I don't know. That's he told me that I just don't know why people didn't solve this problem. Anyway, and this problem can also formulated as
so why do you write those xii and xjj there explicitly? I mean, aren't they all equal to t?
To t, yes.
Yes, so you just...
Yes, you can. You can. Yes, you can. Yeah.
So you're just fixing xij
To the radius. Yeah.
to t minus 1.
No.
Yeah, that's and now
Granny.
probably approach to the last bit, and now you may want to say, all right, okay, there are many such problems. Well, what can you do? Can you provide any new things, a new understanding of such problems? Probably, I can only say that I have more questions rather than answers. And this is one question. So this is, I took it from Laval's 1979 paper, wonderful paper. And I think his initial starting point for calculating this Laplace theta function is from a geometrical embedding. Okay, he start from this. So he called this graph has orthonormal representation if those points are on a unit sphere. Okay, they are unit vectors, unit sphere, and they are orthogonal to each other if the edges belong to the complement of the metric of the graph. Okay, that's his definition. Then, if you do that, if this is the orthonormal representation of the complement of the graph G, then the theta function equals this inner product squared. Okay, this D is also a unit vector. It's also on the sphere. What if you draw a picture? So this is the sphere. You have the point, and some of the point has to be orthogonal to each other, and you want to find a D, okay, another unit vector on this sphere, so that you want to maximize this angle. And this because they are unit vectors, and P1, you multiply inner product between the two unit vectors. Actually, you are dealing with projection. Okay, so actually you are calculating this part. Okay, so that's the projection. If you think from that way, this is the projection squared. Okay, of course, projection is related to distance. Okay, so that's why it's something indicate that squared distance will come into play. Okay, so and at that time, I was amazed reading this paper. Suddenly, Laplace changed to this. Okay, he said that all right, you can use this problem, solve this problem, and instead of doing this one. Okay, and that is the SDP problem, and in his original paper. Now, because this is the projection, all right, this is the projection, and the projection is this is the unit part, unit vector. Projection has two parts, this part and this part. This is Euclidean distance. This is this part, and also you have this part. Okay. Okay. Look, these two. If you want to maximize the cosine, this is the cosine. If you want to maximize the cosine of this angle, you would see this distance and this distance is very close. All right, very close. If you want to maximize that, and under this condition, the D, this vector, you don't know this vector. If the angle is less than 90 degrees, okay, actually this appears in Schreiber's theta prime variant of the theta function. So this is one of his conditions. And if you do that, actually you maximize the projection. The squared actually is equivalent to minimize this distance. Okay, give you the same solution, but we are only talking about a pair. Okay, but the problem is that, look, the problem here is that you want to do the sum. Okay, not just a pair. If it's just one pair, and you have the maximization of projection, you have minimized the distance. This distance is related to this. Okay. But the problem is this, as I said, the definition, the quantity is maximize the sum of all the pairs. Okay. So that proposes they need to consider this problem. So I would ask, what would happen if we minimize this quantity? Okay? And this quantity, a good thing for this quantity is this. They are all distances, Euclidean distances. Look, this is a squared distance, and we quite like it. And they are all on the sphere, and some of the points, they are orthogonal to each other, and that's very easy. This constraint can be translated to linear equations, and simple linear equations. Actually, the sum point distance equals 1, actually. A very simple constraint. So what I would like to ask, if we calculate this quantity, okay, what is the relationship between this quantity and the theta function? So that is my question. So I want to know the answer. So I got the partial answer to that. So if I define, because you are dealing with from minimization to maximization, there's duality, something. So you define another quantity so that the square root of them, the sum of the square root of them, you calculate this. Okay? This is from the convex programming problem. And you calculate this quantity, the sum equals the square root n. And you also need this number, I call it t theta. And this number is this. The SDP formulation is this. You want to maximize the matrix all ones, multiply this, subject to the trace of x equals 1 and xij equals 0 if xij belongs to E and is positive semi-definite. Suppose I have a solution to that. Suppose I have a solution to that. I would like to know the quantity of this. The optimal solution, the square root of the diagonal element, I sum them together. I want to maximize this quantity. Okay? I want to maximize this. And we will see why we need this quantity. So this is the quantity that I would like to calculate. Of course, it's very difficult. I think it's very difficult to calculate. Interestingly, for vertex transitive graphs, this quantity is 1. Okay? For such graph, it is 1. And of course, if you have a theta function value can be calculated by semi-definite programming, you get this number and you define this quantity. It can all be calculated. I omitted the theta here, so this is just a quantity. You can calculate that, and that is what I call the distortion, because you transfer from a projection to distance, and sometimes you have to squeeze the distance. Okay, and this is not equivalent. And for the vertex graph problem, it is equivalent. But other than that, I don't know. Other than that, it has the distortion. So what I can get is the bound. I have this quantity. This quantity is less than this, the theta function, but greater than the theta function multiply the distortion constant. Okay, distortion constant is divided by this. And the thing is, if it is vertex transitive graphs and the distortion distance is 1, there's no distortion. Okay, it's 1. So that's something. Actually, what I think of this distortion here, this distortion d theta actually depends on tau theta, depends on this number, on this. Okay. So what I like to actually to understand is this: people adding, cut inequalities to strength the SDP formulation. And what I want to understand is how much you can improve by adding, for example, triangle inequalities. From my understanding, from this bound, especially for vertex transitive graphs, and I can say that adding triangle inequalities based on distance cannot help you at all. Okay? And actually, this observation has been proved by some papers. They reported that for vertex transitive graphs, if you adding triangle inequalities, this does not help. Okay? And this actually explains why you cannot adding the triangle inequalities. Adding triangle inequalities does not help at all, because you adding or not, the quantities, they are equal, because this is 1. It's always, this quantity always equals theta function. Okay? Of course, I need more time to understand that part. Actually, what I want to understand is this. People talk about a triangle inequality. What are they? And because I'm not expert in using that, I never tried to solve problems by adding the triangle inequalities. I ask myself, what are the triangle inequalities? Triangle inequalities is this. I took it from somewhere. I read the paper. I said this is for the theta function. You add this. Those are the triangle inequalities.
Yeah, that's only half of them, I think. I think that's only half of them.
Half of them. They are more than.
Yeah, those are homogeneous ones, but there's also inhomogeneous ones.
Right. I just took y of this.
Yeah, there's one that's got a right-hand side of 1, another kind.
Okay. So what I try to understand, because when you say
something like xij plus xik plus x.
are you talking about the triangle inequality in max cut problem?
Yeah.
This is for the.
Yeah, but there's a simple linear map.
Okay, right. Okay, right. Anyway, I took it from somewhere, and I try to understand in terms of distance. Okay, and in computer science, there is one metric called the L2 metric. Okay. L2 metric, actually, they're dealing with the squared distance. If the squared, you pick 3 points. If the squared distance obeys the triangle inequalities, they call it L2 metric. Okay? And I thought L2 metric may have something to do with triangle inequalities in semi-definite programming. So this is the triangle inequalities. So what I try to understand is this. Okay, this is the positive semi-definite programming matrix. I decompose it. I use this point as the embedding point. So those are the distances. Obviously, this equals. You substitute to this, and something like this come up. Okay, and I don't know. That's my question. Are the triangle inequalities are L2 metric? I don't know. So I don't know why I want to translate such constraint into distances, but I don't.
There must be some misprint here, because you basically say that the square is positive with the L2 metric.
Which one? The
But one. L2 metric. L2 metric.
L2 metric.
So do you mean that on the right hand side there's pi minus pj?
I think it's
Oh, right. Okay. Pi, Pj. Yes, that's Pi, Pj. Pi, Pj, Pj, Pk.
And then the last
That
line,
is Ik.
yes.
Yes, that's
And then is the last line still correct, or is it because there's a xik on both sides? I cannot believe.
Oh, right. Probably. Yes, that's what I I just inserted this slide. This is my last slide, probably this morning. so misprint. And the thing is that if I use yes, thank you. This if I use this is a PJ. If I use L2 embedding, L2 matrix, the thing is that I want to translate triangle inequality from semi-definite programming into a metric. But I don't know. I don't know if you have the why is called the triangle inequality in semi-definite programming. Why you say I add triangle inequalities? Triangle inequalities for me has to do with distances and where the distance from.
0-1 matrix, right?
Yes.
It's when you want to have triangle inequalities, and it probably helps in problems such as sparse cut.
Yes, I know that a bit. Though, so you pick 3 points, then 0, 1, you add them. You have to something. I would say is from a relaxation point of view rather than from the distance point of view. I'm not sure.
Yeah, so after a couple of years after the Gomez and Williamson paper, there was a paper by some other guys, I've forgotten the names, but they talked about adding triangle inequalities to the relaxation. And they proved that it was equivalent to imposing some kind of bound on the angles.
Right.
Not the distances, I don't think, but the angles.
The angles.
Unfortunately, I can't remember the authors.
Yes.
Sorry.
Okay, thank you. So what I'm trying to understand here is this. I have this bound. I have this distance matrix problems. Anything to do with the distance, for example, triangle inequalities, if you from the distance point of view, and because you are dealing with the distances, triangle inequalities are automatically satisfied. You don't need to add them. You don't need to enforce the triangle inequalities to formulations. And this quantity for the vertex transitive graphs, this quantity equals the theta function. That led me to believe that for vertex transitive graphs, don't add triangle inequalities. They won't help. So actually, as I said, mentioned before, some numerical result people reported saying that for vertex transitive graphs, adding triangle inequalities help little. Yes. I think there is a wide guess. I think because this number actually involves this, it's very difficult to calculate. Okay, probably for some class of graphs, one can calculate, but it's difficult to calculate. And fortunately, we can calculate a theta function. We can calculate this Q quantity from Euclidean distance metric. There's also convex problem. You calculate the ratio. If the ratio is bigger, okay, it's always bigger than 1. The bigger, the more room you can improve by adding distance-related triangle inequalities. So that indicates that if you know the ratio, if the ratio is bigger, then you just add cut inequalities. Then it will help, from my own understanding. So that is those two quantities are easy to calculate. So that's
which triangle inequality would you add?
That's a question I don't have answers. What kind of triangle inequalities?
It could be related to this solution. I mean,
yeah,
to take the 3 largest terms in the sum, for instance, or something like this. So it should be related.
As I said, I investigated such a problem. I never done it for graph problem before. I got a time here, so I thought about something. I thought this for me it's interesting. I would like to understand that. So I haven't got time to think about anything about what kind of inequalities you want to add, what kind of inequality you want to add, how they can help. Such problem I don't know. Yeah. So that's all for my talk. Thank you.
Thank you, and thank you for finishing with these open questions, so that after the
Yeah,
end of the
okay.
program we
Yeah,
have things to think about. Any questions, please? Comments?
May I add another question? Because you talked about embedding dimensions of
Yes.
EDM, maybe.
Yes.
Distance problems.
Yes.
You can also ask a similar question about angle packing. So instead of EDM, you have Graham matrices. You had it already.
Yes. Okay.
So my question is, given you have a non-negative Graham matrix or a doubly non-negative Graham matrix, positive semi-definite, non-negative,
Right.
what is the embedding dimension to get the representation, but not in the full sphere, but rather on the positive orthant intersected with the field? I have a theoretical answer. This is the CP rank of the matrix, but I would like to have algorithms for that.
I don't know. There's one thing that probably related to that. Look, this you minimize this distance, and you drag those distance going to approach one actually. You drag those distance to the origin, and that means if you translate to Schriver's theta function, and that means that equivalent to every element of the matrix to be non-negative.
Yes.
And you don't.
But I need that the P should be non-negative.
P should be non-negative. P should be non-negative. I probably that you mean every component.
Angle packing in the positive part of the sphere.
Okay, that would involve many inequalities, linear equations, linear inequalities. Oh no, I can't say that. I can't say that because you're dealing with the Graham
I'm sorry, I
representation.
was not insinuating that it's very closely related. I wanted to add this open problem.
Yes. Okay. Yes. Yes. I think about that. I think about that. Yeah. Yes.
Any other open problems or questions?
Not a question, but more a recommendation for a book. There's a fantastic book called Geometry of Cuts and Metrics by Michel Desart and Monique Laurent. It's fairly old now, but it gives a great detail on different kinds of metrics and different kinds of relaxations of metrics. And it also explains how they are connected with many different branches of mathematics. And it's not an easy book to read, but anything you want to find pretty much about metrics will be in there somewhere.
Right. Okay. So I will have a look.
So it's Desart and Laurent.
More comments?
Am I allowed a very vague association with John Lee's talk? Most of you remember that he used the unit circle in the complex plane to represent points. And now your talk reminded me that Lovász did the same, but in n dimension instead of 2 dimensions. There could be some relation to this. But this was coloring problems, if you remember, and this is a max click problem or a max stable set problem.
But Lovász's original thing is for also independence with coloring, right?
Pardon?
Lovász's original thing is for also
Yes,
independence.
so there should be some relation. Probably John's approach was a projection on the 2 plane of the no?
I think he cannot use, in complex numbers, you cannot use the absolute values, so you cannot use the complex conjugate. So I think this is a completely different world.
But I thought it in an embedding in R2, but this is not the case. He wanted to have complex
Yes, the complex
polynomials.
structure, yeah.
Sure. So I was just intrigued by the geometric analogy or similarity.
So, thanks to Stephen again.